Okay, now I want to discuss a particular observation that is a consequence of limit theorems for sums of independent and identically distributed random variables, which is the basis on which you can define stochastic processes, and I will be clear about this. So as we have said, if you take the sum of n IID random variables, where this xi are IID, with a certain and let's say that the expected value of x is equal to 0, or that say we take a probability distribution which is symmetric around the origin, where when the expected value does not exist. So that these variables are essentially symmetric around the origin. So this is a sort of we expect that also the distribution of Sn will be symmetric around the origin. Okay. So now, if you make a plot of Sn as a function of n, you will see a certain curve. And essentially the limit theorem tells you that you can write Sn as n to the 1 over alpha times a random variable y, which is finite and is independent of n. So this means that essentially you can rescale both the x-axis and the y-axis in such a way that you can define essentially a curve that depends on a continuous variable t, which you can define as to be as n times dt. So in a sense, if you rescale the x-axis by 1 over delta t, then the idea is that you can rescale the y-axis by 1 over delta t to some power beta, and essentially get a curve that in the limit when n goes to infinity essentially is finite. Okay, you get you can define a curve in this way. So the idea is the following. So that so if you take now if you take a new definition of time as n times dt, when you take the limit as delta t goes to 0, a finite time will correspond to n going to infinity. And then in this limit we expect this to be a random variable which will be distributed, which will have a universal distribution of y. And now if we take, if we define a random variable z of t as the limit as dt goes to 0 of say dt to some power beta times s of n computed in t divided by dt, then we can ask what is the value of beta that I should use in order to get a finite limit. Okay, and because n is of order t divided by dt, So you see that here, if you take beta, which is equal to 1 over alpha, you can get a finite limit, and this finite limit will be of the form t to the 1 over alpha times a random variable which has a universal distribution, which is either a Gaussian if alpha is equal to 2, or is a Levy distribution if alpha is between 0 and 2. Okay. Now, this is interesting because so it allows you to define in a mathematically rigorous form these continuous random functions of a continuous variable, which are essentially the simplest building block of stochastic processes. And you can get what are the main properties of these random functions by just what we know about the properties of sums. Okay? So the first property is that z of t has, so of course z of t is a random function, so it is a function of t and of omega, of the realization of the realization of this sum. So z of t has independent increments. So in the sense that if you take 2 times t and t0, then z of t minus z of t0, okay, if this is t0 and this is t, then this increment here is independent of this increment here, okay? And because this is because this is obtained as the sum of independent terms. So the terms that you sum in this time interval is independent from the terms that you sum in this time interval. Okay, so is independent of z of t. And actually this is true for any non-overlapping interval, so the increment of the function in a particular interval here is independent of the increment of the function in any other interval which does not overlap. So this is what this means. Okay. So the second thing we can ask is whether this function z of t is is defined as the limit as delta t goes to 0 of delta t to the 1 over alpha times s of n computed in t over delta t, and which is essentially t times this random variable t to the 1 over alpha times this random variable. Whether this function is a continuous function. Okay, so first of all, let me remind you that the scale, so this tells you that the scale of this function over an interval dt, the variation of this function will always be of order t to the 1 over alpha. Okay? And now let us discuss whether z of t is continuous. So, of course, let me remind you what continuity means for a normal function. So, f of t is continuous at t0 if for any epsilon positive there exists a delta such that f of t minus f of t0 is less than epsilon for all t which are less than delta from t0. Okay, so this is the standard definition for a function of t. However, this is a random function, so it also depends on the realization of z of t. So we cannot apply this definition here. So we have to apply a slightly more complex definition. And one idea, which looks like unambiguous, is to say that if we want to check whether this function is continuous in an interval, say from t0 to t, then what we can do is to divide this interval in many small intervals, say in m intervals from, so we take a delta t, we take a delta t which is equal to t minus t0 divided by m, and there are m intervals, okay? And then what we ask is that in each of these intervals, the variation delta z in interval I should be less than epsilon for any epsilon. So our definition of continuity is that we say that zt is continuous if for any positive epsilon the probability that the variation in the ith interval is less than epsilon for all intervals from 1 to m. If this integral is this if this probability is equal to 1 when n goes to infinity, because this will tell you that however small a variation you choose epsilon, then there will be no point in this interval in the interval from t0 to t where the variation is larger than epsilon. So there is no jump larger than epsilon in this function, okay? With probability 1, okay? So this is our definition, okay? So now it is clear that this probability, since the intervals are all independent, then this probability is is a product over I from 1 to m of the probability that one of the variation in intervals zi is less than epsilon. But because the size of this interval is the same, then this distribution is also the same. So I can write this as 1 minus the probability that delta zi is larger than epsilon raised to the power n. Okay. Now, in order to compute that limit, what I have to compute is the probability that delta Zi is larger than epsilon. Okay. Now, delta Zi is equal, because of this, to delta Ti to delta T to the 1 over alpha times a random variable y, which has the limit distribution, which is either the Gaussian or a Levy distribution. So this probability is actually the probability that the random variable y in absolute value is larger than epsilon times delta t to the minus 1 over alpha. Okay? Because if delta Zi must be larger than this, then y should be larger than epsilon times delta t to the 1 over alpha. Okay, so for the Gaussian, this is the integral for x larger than epsilon delta. This is for the Gaussian. Delta t divided by alpha is equal 1/2, so this is divided by delta t squared. Of dx square root 2 pi e to the minus x squared over 2. Now this delta t is going to 0, so this integral is going probing the tails of the distribution, okay? Because delta t is going to 0, and actually delta t is of order 1 over m. So if you do this integral, you can show that this integral is less, for the Gaussian, is less than e to the minus sorry. Sorry, this is n to the alpha, okay? Sorry, this is n to the alpha, so I should take this equal to alpha, and this is equal to alpha. Sorry, I got confused with the alpha and 1 minus alpha. So this is divided by delta t to the 1/2. So this is essentially e to the minus is less or equal than e to the minus epsilon squared times delta t, which is t minus t0 divided by 2m. Okay. So now you see that you can use this result here. So sorry, this is delta t is at the denominator, so it should be m divided by t minus t0. Okay. Okay, so what you can see is that this probability essentially goes to zero exponentially fast in m. So 1 minus something that goes exponentially fast to zero with m raised to the power m essentially converges to 1. Okay, as n goes to infinity. And so what this shows is that for alpha equal to 2, so when we are dealing with the central limit theorem, then zt is continuous. So in this case, zt is function zt is called the wt, and it's called the Wiener process. Okay, because of Wiener, not because of it was invented in Vienna. Okay, so we have concluded that for alpha equal to 2, z of t is a continuous process. Now we can do the same argument for alpha less than 2. Now for alpha less than 2, we have the same argument, but here, when we do this integral, we have to take into account that the probability distribution of y goes as, so this probability goes as y goes to 0 with a power law. Okay? So, so for alpha less than 2, the probability that y is larger than some z is essentially goes as a constant times z to the minus alpha when z goes to infinity. Okay? So in this case, you see that this will be of the order of a constant times epsilon dt to the minus alpha to the power alpha. So it's essentially of the order a constant times epsilon to the alpha divided by dt. But now dt is t minus t0 divided by m. So this is t minus t0 times m. Sorry, to the minus alpha. So this is epsilon to the minus alpha times dt to the minus 1 times dt. So this is the converse of this. So let me rewrite it. This is a epsilon to the minus alpha times delta t, which is a epsilon to the minus alpha times t minus t0 divided by m. Okay? Now, when you put this relation inside here, then you see that this is 1 minus a constant divided by m raised to the power m. So this converges, in this case, to e to the minus this constant a epsilon to the minus alpha times a t minus t0 divided epsilon to the alpha. Okay? So in this case, you see this probability is less than 1. Okay, so that there is a finite probability that there is only a finite probability that there is no jump. And also the interesting thing is that this is also the form, if you see, this is also the form of the probability that a Poisson random variable with mean a t minus t0 divided by epsilon to the alpha is equal to 0. Okay, so the probability that there are no jumps is equal to the probability that a Poisson random variable with this mean is equal to 0. So this tells you that indeed for alpha less than 1, for alpha less than 2, the trajectories that you will see will have jumps. There is a probability that they will have jumps. And you can refine this argument and see that the probability the probability that you get a jump is exactly given by a Poisson process. So jumps occur independently in this, and the probability that in a given interval you have k jumps larger than a certain epsilon is given by the Poisson distribution. Okay? So the last, and of course, now if alpha is if alpha is between 1 and 2, these jumps will be essentially small. But if alpha is less than 1, then these jumps will account for the total variation in the sum. So the total variation between time 0 and time t will be essentially dominated by very few jumps, actually by the biggest jump in this interval. Okay, so the last thing you can ask, always using the same argument. So if you take the Wiener process, so this process when alpha is equal to 2, then you can ask whether it is also a differentiable function. Okay, so you can ask whether it is a function such that the derivative is finite. Okay, so but the derivative is essentially the limit as h goes to 0 of z of t minus plus h minus z of t divided by h. So essentially you can ask this question by studying what is the limit as h goes to 0 of the probability that z of t plus h minus z of t divided by h in absolute value is less than k for any positive k as large as you want. So this will tell you what is the probability. It will give you an idea of what is the probability that the derivative in t is less than k, or is bounded. Okay, And you can find, you can do this integral with the same idea that we have used before. You can find that in the limit when h goes to 0, this limit is equal to 0. Do it as an exercise. And what this tells you is that the Wiener process is nowhere differentiable. Okay? Okay. Okay. And okay, so you see, to summarize what we have said in this lecture. So the existence of limit theorems for sums of independent and identically distributed random variables allow you to define continuous stochastic functions which have very specific properties. So in particular, when you are in the situation where the variance of the increments is finite, then you are in the basin of attraction of the Gaussian, you are in the central limit theorem regime. And so what you find is that the trajectories in this case are called the Wiener process, and these are continuous trajectories which are nowhere differentiable. If instead alpha is less than 2, you have the increments of power law distribution with an exponent alpha which is less than 2. Then you have what are called Levy processes, and these Levy processes are not continuous, and when alpha is less than 1, essentially the total variation, so the total variation of these trajectories is given by just few jumps, and the jumps occur. The number of jumps that you have in any interval is essentially distributed as a Poisson distribution. Okay?